Different materials can be transparent to one frequency but opaque to another. Ultraviolet, right? Glass is opaque to ultraviolet. It is transparent to visible, but infrared, it's like a mirror. And we're talking about a greenhouse, because what happens to infrared light inside of our greenhouse? Remember, visible light comes into the greenhouse, hits the objects inside, is re-radiated as infrared. Can that infrared get back to the glass? No. The glass doesn't really absorb it, it just kind of reflects it back in. This is why your car gets so hot inside. Because that visible light comes in, hits the interior of your car, is re-radiated out as infrared, and it just keeps heating up and heating up like a greenhouse, runaway greenhouse on that. But if we looked at other things, like this room, now it's opaque to visible light. But if we saw in the radio frequencies, we saw in radio, this room would be like being in a glass house, because all the walls, everything in here would be transparent, except really where the metal was, where there was metal, be transparent. Maybe parts of your bodies would be also opaque to the radio. We saw in x-rays, you would see a very faint outline of your flesh, but you would see your bones. Because bones are opaque to x-rays, but your flesh is mostly transparent. Pardon? So different frequencies. So don't think because something's like glass is transparent to one thing. It's not transparent to everything. Just like our walls. They're opaque to us in visible light frequencies, but they're not opaque to other frequencies. So you really have to define what frequency. Questions? Which leads to the shadows, which is the second thing and last thing we're going to talk about today. Shadows. Shadows have two parts. We have the umbra, which is the dark area of total shadow. In other words, all of the light sources being blocked. This would be the area of total eclipse for a solar eclipse. If you are in the area where there's a total eclipse, you are in the moon's umbra. Then you have the penumbra. The penumbra is the area of partial shadow. Part of the light is blocked, part is not. This would be like a partial eclipse. The area of partial eclipse is the penumbra on that. And we'll need more time. Good? Need a little bit more time. We're good? So, sharpness of the shadow is going to depend on the size of the object compared to the size of the source. The apparent size of the source, I should say, and the distance from the source, how far you are. It's kind of like, remember, the moon and the sun. As observed from the Earth, the moon and the sun, how does their size compare to each other, as observed from the Earth? How big is the moon and the sun in our sky compared to each other? And we'll go right out looking at the sun. Anybody know? Talked about this before. The moon and the sun are basically almost the same size. As observed from the Earth, they appear to be almost the same size. This is why the moon just barely covers the sun during a total eclipse. Just barely covers, but they basically are, as observed from Earth, they are the same size. But we look at this shadow here. Basically, the source is very close. We're very close. Right here, the source is very close. And it has very little penumbra. This little edge, this little fuzzy edge. That's the penumbra. This big black area is the umbra of that. But as we pull the light source back, notice what's happening here. The area of fuzziness is getting bigger. Our penumbra is getting bigger until we have a little bit of umbra here in the middle. We have a lot of penumbra. So the penumbra is that fuzzy kind of area on there. And then we need more time on the slide. So with our rolling pin, our pin is very close to the screen. Notice, is there really any penumbra here? No, it's pretty much all umbra. As we pull the pin back toward the light, toward the source, more of that source can get around it. Notice we're getting more light around, and eventually, notice even this one, it's almost all penumbra there as we get light around it. That's because it's not blocking everything. When it was close to the wall, it could block out everything. Another thing to consider, like for planets. You really have cones. The shadow is really like a cone, and it will eventually end just because of the way the sun comes down. You get to a point where the shadow is not there on that. But you basically have an umbra cone and a penumbra. So it's like if this was the moon, when the Earth intersects that part, you would get a total eclipse. If the moon moved into the Earth's shadow, it moves into the umbra, we get a total eclipse of the moon. Things like that. So how exactly does that work? So we have the sun, there's the moon, they're kind of exaggerated here. So the top of the sun, we have rays of light coming off the top of the sun, like this. You have rays coming off all parts of the sun, actually, but we're just going to take the top and the bottom. All right. So, notice the red rays. Here are the rays from the red come down, the blue come down. Where's the only place where both sets of rays are being blocked out, Fernando? Where's the only part where they're both being blocked out, the bottom and the top? Notice these rays are being blocked. Those rays are being blocked. The only place that they kind of overlap is right here. And if this was our total eclipse, that would be the umbra of our total eclipse. Notice the top and the bottom are being. But notice the shape. It's kind of like a cone. Now up here, if I was up here though, are the rays from the blue part, the bottom being blocked? Are blue rays being blocked up here? And look. The bottom part of the sun being blocked out by the moon? And the answer would be yes. But is the top part of the sun being blocked out? No. So we have some blocked out, some not. And the same thing in the bottom. The red part, the top part is being blocked, but the blue part is there. And this was what would give us our penumbra. There, that area where some is being blocked and some is not. Some is being blocked and some is not. This is how our eclipse shows up. Questions? Questions? All right. We're going to do our little exercise right here. Now, do not make this harder than it is. And do not look at the sun. All right? Do not look at the sun. We are basically making a pinhole camera. This is what astronomers do to just study the sun, because they can't really directly at the sun. Even with special filters, it blocks out so much they really can't gain detail. So they actually project images of the sun in order to do this. And that's what we're doing. We're working with the image. So you guys are going to poke a hole through a piece of paper. And you can take one of the bigger pieces of paper, don't little one. But all you need to do is kind of take your pen